If everybody wants to move up, there's actually be a live demo. There's a webcam pointed towards you. Nothing's recorded, but it'll be part of. This is a vision talk, so we'll do some live demo, see if it works. I've actually never tested it in this room, so it'll be a surprise for me too. So I'm going to be talking today about fine-tuning vision foundation models. I work at a company called Apella. We do surgical operation room improvements. So we use artificial intelligence and computer vision to create these predictive models which allow you to improve the productivity of operating rooms. We do this through having cameras, 4 walls of the operating room. We combine this with historical data and EHR data, and we use this to provide predictive models which provide real-time feedback to the users of people in the operating room, as well as the charge nurse and everyone throughout the hospital. You can get insight data, you can get real-time data, and the whole goal is to make sure that cases start and end on time, people get home on time from work, the patient gets home on time, everything goes smoothly. That's the last I'll be saying about Apella for this presentation. The rest of this is going to be more on things that I can publicly present. What I want this presentation to give you is, if you haven't used vision foundation models, or if you haven't fine-tuned those, to give you a starting place for that, to give you some best practices, as well as a code base. So at the end of this presentation, there's going to be a code base link, a QR code, and also all the slides in this presentation can also be accessed from that QR code. So you don't have to take any notes or anything. What I hope you'll remember, so if everyone gets distracted during a talk, if you can pay attention for this one slide, these are the 3 things I hope you'll remember, and afterwards, check your phone, do whatever you need to do. The most important thing is not the fine-tuning, it's the data that you're using for the fine-tuning. You really want to have really high-quality data that's really specific to your application. That's going to make the difference in terms of how well things perform. The models change really quickly, the techniques change pretty quickly, but it's the data that you have that you're continuously gathering, even once it's online, that's going to make the difference in performance. Fine-tuning is actually pretty easy. We have very talented people developing algorithms, and a lot of people just applying those algorithms. It works well. The more difficult part is the deployments. So this is an MLOps conference. There's a reason for that. Deployments are difficult. Affordable deployments for things which require GPUs are really difficult, especially when you're getting into the video and level of vision models. Okay, let's go to the live demo. So for this presentation, what I did was I took an open source foundation model, one of the latest ones that came out from Meta, the VJEPA2 model. Came out in June. And then I fine-tuned it on a research data set from the NTU lab in Singapore. And I fine-tuned it for 3 things: sitting down, standing up, and waving. So there's more latency due to the network connection here. You can see the network time here. The GPU time is quite fast. The actual response time is good. But can I get a couple of people to just wave in the camera? And we'll see. There we go. It's picking up waving. Good, good, good. Would anyone want to stand up, stretch your legs? Let's see how long it takes to pick this up. So it's doing 1-second video increments here, and it's sending it, and there's a long network latency to this. When I was testing this at home, it's quite a bit faster. So at some point, I'm hoping it's going to pick up that 1-second video clip of people standing up. Others, things that everything else that you're doing, which it's not trying to recognize. And if everyone wants to sit down slowly, we'll see if it detects it. Yeah, it's a 1-second video clip, so it's catching before and after. For these video clips, I chose 16 frames, and I'll explain where we came about from 16 frames for the video clip. And then it's sliding windows of 1 second the whole time, so there's no overlap between the windows. And I'm curious if it's going to change it. Went to waving.
But it did pick up sitting down because it went up to 13%.
Okay, good. Yeah, it's interesting because with this, any other activities, how it's weighting things. So that was made just for this presentation. I like this guy. He's repeatable experiments. Thank you. Let's get more than one in. So that's the demo. This is trained for this. Training the model for this is pretty straightforward. Deploying it was a little more difficult. I put this on a Cloud Run function. They have GPUs now for GCP, for Cloud Run functions. And so I had to warm this up before we started doing this, because otherwise it would have taken longer. And I'll describe a little bit about that later in the talk. But so the point was that basically like you can get to pretty quickly a working model. This was action detection. This is trying to detect a specific action of y'all in the audience, right? There's a lot of applications for vision. And I'm not going to describe all of them, but I'll describe some of the most common ones. One of these is, the most obvious one is basically recognizing text in written form from images, converting that. Object detection is also a huge one. You have various forms of this. Some are domain-specific ones, like medical imaging. You have autonomous vehicles, very, very big. Very in vogue right now is all the generative options. So you have the image as well as the video generation. You have a lot of applications when it comes to, like, in these industrial companies, when you're manufacturing something, there's a lot of defect detection using vision of some sort. And of course, question and answering. I'd say that one, at least in my opinion, has the furthest to go still. It's that combination of the multimodal things where you have the video. We've tried out a lot of things to get information from videos in textual form, and like even the best models out there struggle with it. So I'm going to start the talk. There's going to be two large sections. One is fine-tuning, the other one is deployments. I'm going to start with the fine-tuning part. First, I just wanted to address like when should you actually consider fine-tuning. It's not for everything. It's really, I'd say the most common use case is if you have an output that you need that the model itself doesn't provide you with yet. That's a good case for fine-tuning. So a common example of that is like you've got a generally pre-trained model and you need to train it to classify something new that it's never classified before. You have specific things for your product you want to classify. That's a very common use for fine-tuning. If you start to use using timestamps in videos for some reason, image segmentation. Another thing is if you have very domain-specific video or images, like medical fields, very common for this, but also autonomous vehicles. You're going to run into things which are domain-specific there, which you can improve model performance for. The last one is just like you have an application. Maybe it's still a sort of general thing. Maybe it's a general classification for a product for retail or something, but it just doesn't perform that well based on the pre-trained model alone. If you've got your own data, try it out. It's not that hard to pre-train and evaluate a model. Fine-tune and evaluate a model. For training data set collection, really collect your own data as soon as you can, and then keep gathering it. There's two reasons for this. One is that your data is going to be the most representative, obviously, of your problem. But also, these models come out so quickly. Like the state of the art is moving very quickly. And so you want to have a data set on hand which is representative of the problem you want to solve, that you can quickly evaluate a state-of-the-art model with. The other options are publicly available data sets. This is nice for just quickly benchmarking something. I used for this demo the Rapid Rich Object Search Labs data sets. This is the NTU Singapore labs. They kindly provided this. This is for research use. And then you can also purchase data sets for Shutterstock and Getty Images. I'm less familiar with this, but maybe it's useful in some cases. Throughout this topic, I'm going to pepper in video vision sort of tidbits, things that you have to pay more attention to for video, which if you're used to using image-based vision models is less important. One of these is sampling from videos. There's two general forms of sampling from videos. One of those is uniform sampling. The other one is event-weighted sampling. Uniform sampling is very simple. You just say, take this many frames from a video clip and intersperse with the same interval the distance between frames. Straightforward. If you have a balanced video where like things happen at about the same rate throughout the video, it's useful. Or if you have a very dense video where it's just a very short video. If you have longer videos or you have things that are happening in the video which are not distributed evenly throughout the video, you may want to explore event-weighted sampling. So for example, like we were doing the demo, right? Most of the time it was like other, right? People were just sitting around. And at some point, people would raise their hand, stand up. Thank you very much for participating in that. And so if we did like a long video where I was recording for an hour before this even started, you'd have this one 30-second chunk of activity. So if we were going to annotate that, we would go back through, take that video, and annotate when that point was, and then sample really heavily around that, so that we could train, fine-tune the model with that. So that is event-weighted sampling. Those are the two general techniques. The other thing that you may have to deal with related to long videos is trying to keep the memory. So really, most of the models out there, even the really state-of-the-art ones that are closed source, which are commercial, are like an hour. You can give it an hour, and even then it's sampling at most. I've seen 1 frame per second at an hour. And so we haven't really gotten to the point where we're able to effectively use long videos for vision foundation models. There are some techniques out there and they're continuing to improve. The two general ones that I've seen are this recurrent hidden states versus cache representation. I'm not going to go into detail on this. I provided a link to the articles. One is more focused purely on vision, and this one is using recurrent hidden states, which meaning that you're retaining that sort of memory about what has happened in the past within the model itself. So within the model, you have that memory. The other one is cache representations, where you're basically caching something into an object outside the model architecture itself. And then you keep feeding that back in every iteration. And you update the memory with the past memory, run it through the model, update it to form a new memory, and you keep doing that throughout. So related to, we just talked a little bit about these are specific things that you're looking for in your foundation vision model. The other things which are very general about looking for things in vision foundation models are like the licensing. Licensing, you want to ideally have an open source model if you're going to be using it for some sort of commercial application. Maybe a copy left is appropriate, meaning that you train the model, and then you have to, again, share it so that other people can use it. And then there's research only, where you can't commercialize it. Types of data, that's really important. What data the model trained on is very important. Obviously, images versus videos, but also resolution, frame rates, what did they explore? Multicam, that's definitely a specialized area. Also the domain with which, from the data that it's taken from. This is going to really impact which model you should choose for your own projects. Another is performance. You just want to say okay, these two models look like they could work. What's the relative performance? A lot of times, the people who are developing these models do use benchmarks. Do be careful about how they actually do these benchmarks. There's a lot of different ways you can evaluate a model, and it'll bias things. And so make sure that when you're comparing papers, that you're doing apples-to-apples comparisons. The last one is CPU versus GPU inference. If you're doing video, you're very likely going to have to use GPU. For some imaging, you can still use CPU. If you can use CPU, it's really much, much more affordable. It's obvious, but it's still worth stating that if you have slightly worse performance in a smaller model, but you can use CPU with it, I would say see how far you can get with that CPU, because you're going to be able to run a lot more operations through it. Okay, so for the live demo I did here, I used the VJEPA 2 architecture. I'm going to introduce this at a high level. And this came out in June. This came out from Meta. They wanted to make something which was, in their words, like a world model. They're trying to actually understand and capture more physics and things. The way they approached this is that they masked videos, and then they had unmasked, and they had the encoder. This is the thing which is going to become the backbone that we use for our actual inference system. And they produce predictions from that. They use a predictor, which takes the embeddings, and then compares that to the EMA encoder. That's the one which has the full visibility of all the patches within the videos. And then they compared those, and then they update the loss, and then they go back and they update the encoder from that. And then the EMA encoder is sort of a lagging, updated. It's sort of a teacher model, which gets information from the student a little bit afterwards. This thing has been self-supervised on an enormous amount of data. And so it's 1 million hours of video and greater than 22 million videos. And so it's likely this is a strong backbone to start from. And especially for the demo, I just wanted 1-second videos. I felt like this was a good place to start. you can take the pre-trained model, and then you can apply it to a lot of different applications. The one we used for the demo was action detection. That's the middle column or row here. And then you can also use it for language alignment, so this is video question and answering. They're also really interested in applying it to robotic applications. And so this is where you're trying to have a robot with as little data as possible learn how to interact with the world. I think this is a great model, did a good job, and when I've been testing it on things, it works pretty well. So that was the specific model, moving from the modeling choices, so the choice of a pre-trained model, to the actual fine-tuning techniques you're applying to that pre-trained model. I categorize these into 3 general categories, like how long it takes to actually fine-tune your pre-trained model. You can have short, medium, and very long. So short is things where you're restricting what you're fine-tuning. It could be 1 to 2 final layers of your architecture for fine-tuning. Bitfit, so this is where you're just adjusting the biases, not the weights of the model. Normalization layer fine-tuning, as well as input tuning. It's where you're just adjusting the input and fine-tuning that, and you're not touching the architecture. This can be good for decent for small data sets, but for large domain shifts, it's going to be pretty limited in what you can do with this type of fine-tuning. Industry standard is LoRa. This is low-rank adaptation. This is very fast. You can almost put it into the short training time. And it just depends on how many adapters you put in the architecture. And it works really well. There's tons of variations on this for different applications. Gradual unfreezing is usually where you start at the end of the architecture and you unfreeze a layer, fine-tune that, see the performance, and keep fine-tuning layer after layer and moving onwards. And so then you can sort of choose how long it takes to fine-tune things. The last one, which is relatively uncommon, is just fine-tuning the whole architecture. This is unrealistic for you unless you're a big lab. You have a lot of data and a lot of compute to throw at something. So the first, I just wanted to give like a simple, we have an architecture. We want to update its classification on the output. So this is fine-tuning strategy 1. This is the simplest one I can give you. This is taking the VJEPA backbone. It outputs video embeddings. They provide, so the meta team provides this VJEPA to attentive pooler. So what this is doing is it's pooling the embeddings. You can pass this into a classifier, and you can use this to produce your predictions. So in this case, we're just fine-tuning the classification layer at the output. Very straightforward, very easy to do. And there's the code base that I'm sharing at the end of this shows you how to do that. And so you can quickly take the VJEPA2 model, download it. It's 1.4 gigs for the smallest of the models. And you can try it out with your application. The next one I'll go into is LoRa. This is something which you're likely to move to quickly if you are to want to invest more time and see the performance increase. The underlying math behind it is not that complex. I'm going to spend a little bit of time going into it just so you can see where the benefits are coming from. This is in the realm of parameter-efficient fine-tuning. And so what we're trying to do here is we're just trying to reduce the number of parameters we have to fine-tune in order to maximally improve the performance of the model. And so normally on the left-hand side of this, what you can see is that this is our normal updates to our weights. What we do is we do backpropagation, we find our updates, and then we add that to the existing pre-trained weights. That's normal. This is if you're going to update all the weights, this is how you do it. LoRa says, well, how can we reduce the number of parameters we need to update? And so what they did was they cleverly made as small matrices as possible, so you reduce the number of parameters. And then there's 2 of them, so you can do matrix multiplication to arrive at the final one. And so you're just updating the parameters of those 2 small matrices, and then you multiply, produce the final one, and then add that to the pre-trained parameters, just like on the left. And the rank is referring to this inner dimension between the 2 matrices. And so the smaller the rank, the fewer the parameters. You do want to, the sort of more challenging thing is to figure out where to add this. If you're using a transformer, I'd say this is pretty well solved for you. You want to add this at the projection. So there's the query key and value projections in a transformer, as well as the output projection. These are large matrices, and this is where you're going to find the biggest bang for your buck in terms of fine-tuning. And so you can apply LoRa to that. What we're seeing in the red box on the top is the original frozen weight matrices. and then the LoRa, those two A and B matrices in that green box. And so we are fine-tuning those smaller matrices, and then we're adding those to the pre-trained weights. We input that into the multi-head, and then we do have an output projection as well. And so that rank we talked about earlier, this is something which is a hyperparameter. So you can explore different ranks. So in this case, there's this value for alpha that you can choose whatever number you want to for it. The important thing is that alpha over rank is the ratio which weights how much you're multiplying the LoRa matrices by. So the bottom of this shows this WX plus alpha over rank times BAX. And so it's basically saying, it's sort of like in terms of loss, you're effectively how strongly you want to have these fine-tuned weights affect your pre-trained weights. And so in this plot, what we're seeing is the average F1 score. This is using that demo model. And then this is, I think, probably using like 50 videos for each class. And then we have the LoRa rank on the x-axis and the F1 score on the y-axis. And this is a rank of 8. The ratio is always 2. But this means that there's a lot fewer parameters that you're fine-tuning when you have a rank of 8 relative. And as you go from 8 and higher, you keep increasing the number of parameters you're fine-tuning. And there's a bit of a sweet spot at 32, but it'll totally depend on your application and how much data you're training with. And this is a performance comparison of that strategy 1 and strategy 2. Strategy 1 was the classification layer only fine-tuning, and then strategy 2 was the LoRa and also the classification layer fine-tuning. And so what we see here on the x-axis is the number of videos used per training, and then the y-axis is the F1 score, the average F1 score across all of the classes. And so what we can see is that there's a bit of better performance just for the classification layer at low numbers of training data, and then as you increase it, you see better performance for LoRa. And this makes sense. Basically, the smaller amount of data you have, the simpler the technique you should be applying to it. The fewer number of parameters you should try to be updating for it, because there's just a limit to how much it can learn. Another hyperparameter you should consider is the batch accumulation. I bring this up mostly because unless you've worked with videos before, you may not have encountered batch accumulation. Videos, when you're doing fine-tuning, you can't fit a lot of videos into the GPU RAM. And so you have to do this stepwise iteration on each video. And so you get the gradient for each video, and then you just add it to the gradient of the previous video, and you create these sort of effective batches, these virtual batches. And so in these cases, on the x-axis of this plot, this is the number of accumulation steps we use. So the number of videos we use per iteration for updating the fine-tuned weights. So for 1, going to 2 to 4, you see like a sweet spot at 4. That means that there have been 4 gradients added up for the update at the accumulation step of 4. And this ended up producing the best result. I go through this in terms of just trying to highlight those hyperparameters you should focus on. And then frames per clip. So if you're using videos, you're going to have to consider how many frames per clip. The right side plot shows you this frames per clip as a function, or like time as a function of frames per clip. And just showing that this is quite linear. The more frames you're using, the longer training is going to take. And so you should try to find the fewest number of frames you need for your performance. This will depend a lot on the length of the video. So take that into consideration. You're going to have to play around with these numbers. They depend on your domain, the length of the videos. Obviously, if you're using images, completely different. But yeah, explore these. These are pretty quick to explore. You can do this all in less than a day. And then a short summary is I would say you can start with LoRa. If you're doing a classification change, just go ahead and update the classification layer. See how that does, especially if you have a small amount of data. Evaluate the performance with increasing amounts of data. Evaluate the number of frames and the accumulation steps for videos specifically. And then tune the usual hyperparameters, learning rate, and the number of epochs you're using. For reference, we used 5 epochs for this, and we picked the best model performance for the demo. I got not a lot of time left, so I'm going to breeze through this slide. If you don't have edge devices, this slide doesn't matter to you. The short story is that there's a big trade-off between using edge devices and cloud. There's a perceived Goldilocks solution where you have like a bit of things on edge devices and a bit of things on cloud. My opinion on that is that you have to become an expert in both. So it's not as simple a let's do both thing. So I would generally say like start in the cloud, it's gonna be easier. And then you can continue to move things to the edge to improve efficiency of things as necessary. There's a lot of trade-offs involved in this, but that's my conclusion from this slide. Back to videos. For video chunking, similar to the frame sampling, you can have like uniform and non-uniform frame sampling. For video chunking, you can have uniform and non-uniform frame video chunking. So uniform chunking is just what it sounds like. You set how long of a video clip you want to use, and you can use that, and sometimes you can overlap it. And the alternative is to say, like, we're looking for some sort of thing in the video which demarcates the beginning or end of a video. And so you can use object recognition for this. You can use color histogram changes. And then you can sort of more intelligently choose what chunks, how to create a chunk of video for fine-tuning. This is for deployments as well, like when you're trying to detect something or give some sort of feedback based on a video. Big considerations is the static's really easy. I would start there. The dynamic is much trickier, and also there's also risks associated with it, depending on how good of a job you are at able to detect these semantic changes in the video. Okay, so for architectures in general, now I'm talking at like even a higher level or beyond the video and edge or cloud. We're talking about just the architecture. What you want to consider here is like, well, how like latency is going to be your deciding factor, and what type of architecture you usually choose. And so latency will force either increasing or decreasing complexity in your architecture. So if you can, if you just need to do batch scheduling, that's great. That's a simple world to live in. The next like faster version of an architecture is going to be something RESTful. It's a little bit more complex, but it's not bad. Event trigger allows you to do more asynchronous communications. And so it's pretty useful, pretty powerful, and decreases latency. And the fastest is if you stream everything. Everything is streaming. That's more complex, but it's very, very fast. And so I would sort of go from top to bottom if you have the opportunity to. I would not start at streaming. It's a complex place to start at. This is a visual representation of the four frame architectures that I just described. The thing which I want to highlight is in the middle, it's all the same. It's pre-processing and classification, or some sort of video processing you're doing here. It's these different things, these different architectures are going to have different things you start usually at the beginning. So for batch, you're going to have the scheduler with the batch ingestion. For the REST API, you're going to have a client talking with it, and usually you're going to be waiting for a response. And then for the event-driven, you can do things asynchronously where you submit it to some sort of topic, go from there. And then video streaming, for example, from like a security camera or something, you're streaming there, and then you have things streaming and updating. Outputs can vary in terms of what you're updating from the classification service or whatever service you're using that the model is running on. Databases are very common. Event-driven may use an async callback, and then you could have a response that feeds back to the client or camera as well. This demo used on-demand, an on-demand deployment, which means that we sent a request, and then it had to spin up a machine. In this case, it had to spin up a GPU machine, and before it could actually start doing anything. So this is useful if you can, it saves money if you can do it this way. But it's very common to also have always-on deployments if you have a lot of requests coming in, and they're pretty well distributed, pretty evenly distributed. There's things in between, which are like during peak hours, you have on-demand, and then during off hours, you have, but during peak hours, you have always-on, and then off hours, you have on-demand. I will note that this cold start problem, that's really going to be a bad experience for a user if they're waiting for something. You can see that it's over 200 times faster for a warm start for a GPU. So once that machine is ready, it's so much faster. And then the CPU versus GPU comparison is also stark. If you need GPUs, you can get, in this case, more than 70 times faster responses using a GPU than a CPU. Yeah, so what I hope you remember from this talk, that's the deployment side of things. Continuously gather high-quality data. That is the most important thing. Fine-tuning itself, it's pretty easy. The affordable deployments, that gets complex, and there's a lot of levels of complexity to it. And with that, I want to thank everyone. Thank you for participating in the demo, and Apella for hosting me for this event. We're hiring, so please check out the careers page. Meta and VJEPA2 team for open sourcing this model. The research data set from the Rose Lab at NTU in Singapore. The conference committee, everyone for organizing this. AV, thank you very much. And yeah, if you can reference the slides as well as the code that was used for the demo using this QR code or the HTML. Yeah. Thank you.
We have time for one question.
Yeah, go for it. The person who raised their hand. OK.
Thank you. Yeah, so in the dynamic video chunking, you mentioned there are risks associated with it. So can you talk us through maybe one example of the risks and then how to combat it?
So dynamic chunking, yeah. So mostly it's like how reliable is your detection of a semantic event in your video? So if you're trying to detect an object, what confidence do you get for detecting that object in the video, which is going to indicate the beginning of when you should start that chunk? You can use, and like the risks, I would say, is like if you use like a color histogram for identifying background or large changes in what's seen in the video, that could be a lot of things. And a lot of the times it's just not relevant to what you're trying to detect. I would say that's only, in my mind, the way that's really useful is if you are trying to segment like Hollywood videos into things and they have big background shifts, then that's pretty useful for that. So you need, for that to work well, you need a good pre-processing step. You need something with high confidence that is detecting the correct thing for semantically chunking your data.
Awesome. That was the end of the session. We will start in a few minutes with the next one, but please first another round of applause for Zac.